Hello everybody and welcome back. Let's talk about the problem largest component size by common factor. I'm going to explain the DSU or the union find approach in detail along with the intuitions of how to actually think about this problem, how to implement the brute force solution, as well as how to optimize it along with a couple of intuitions and observations required to finally complete the solution. Alright, super excited to bring you this one, so let's get started. Before we start talking about the solution, let's talk about the problem statement itself. We're given an integer array of unique positive integers called nums. And we have to consider a graph in which there are a bunch of nodes. So in the case of nums as 4, 6, 15, 35, we have all of the nodes as 4, 6, 15, and 35. So all of the nodes are simply the elements in the array. There's also one more condition, which is the most important one. There is an undirected edge between nums of I and nums of j. So between any two numbers, between any two nodes, if and only if they share a common factor greater than 1. Alright, let's understand what's going on. In the case of 4, 6, 15, 35, we can connect 4 and 6 because they have a common factor 2, which is greater than 1. So 4 and 6 will indeed have an edge between them. Similarly, 6 will be connected to 15. That's because they both have a common factor of 3. Similarly, 15 will be connected to 35 with a common factor of 5. 15 will not be connected to 4. Right? There is no single edge between 4 and 15. That's because the common factors between 4 and 15 is 1. Both of these are co-prime numbers. Alright, so the problem is fairly simple in what's given to us. The goal of this problem is to return the size of the largest connected component in the graph. In the case of 4, 6, 15, 35, the largest connected component is one single component of the size 4. In the second case of 20, 15, 9, and 63, we see that there are two connected components, each of size 2, so we can return 2 as the answer. Alright. Enough talking about the problem discussion, let's actually jump into the brute force approach. Alright, let's start talking about the brute force solution. Since the goal of the problem is to return the size of the largest connected component in the graph, we must first know what a connected component is. Now, if you have been following my channel, you already know what a connected component is, and we have already solved a couple of questions based on that, because it relies entirely on the data structure called disjoint set union or union find. I'll link to a video up here and you can go look at that if you're not familiar with this. But I highly recommend you go through this because it's a fairly popular one used in graph-based questions. So now that we have the disjoint set union data structure in place, we can finally start talking about this line over here. Because this line says that there is an undirected edge between nums of I and nums of j if they share a common factor greater than 1. So this obviously hints at the use of greatest common divisor or GCD, which we'll have to go and deal with. But also, this nums of I and nums of j points to an interesting point. The algorithm we're looking at is order of n squared, because to iterate over all the nums of I will take order of n time, and iterating over all the nums of j will take order of n time again, and both of these have to be nested loops for them to be able to be compared. Which means that we're looking at a very bad solution in terms of space-time complexities, but will be an important one to build our actual optimized solution on top of it. Now, if this still feels a bit off to you, let me actually go ahead and demonstrate. When it comes to the brute force solution, we'll go ahead and take a simple example, which is 21, 10, 5, 4, and 49. So these are 5 elements given to us, and we have to find the largest size of the connected component. That's fine. This is just the problem statement and a sample test case. So what are we going to do? We're going to take the first number, which is 21, and we're going to ask the question, hey, given the number 21 already, what are all of the numbers that I can connect it to? What are all of the edges that I can form from 21 to all of the other numbers in the graph? So given 21, can I form a link between 21 and 10, 21 and 5, 21 and 4, 21 and 49? I'm going to go ahead and compare all of these numbers and find their greatest common divisor. Once I do that, I find that 21 can only be connected to 49. That's because both of them share a greatest common divisor of 7. which is greater than 1. Rest every single pair is going to give me a GCD of 1, which is not going to help us any of. So we'll just skip that. All right, so now that we've considered 21, what do? We'll move on to the number 10. And we'll do the same computation again and again. We'll look at 10, we'll look at all of the neighbors, we'll look at all of the numbers that can be connected to 10, and we'll try to find their GCDs. Now, after we do this computation for 10, we find that 10 gets connected to 5 and 4. Similarly, we'll do this for 5 and we'll do this for 4. Nothing too special, is just iterating over all the values in 2 nested loops. So one loop and another loop inside of it nested. Once we're done with this, we'll realize that there are in total 2 connected components. One is this 10-4-5 chain and one is this 21-49 chain. And so what is the size of the largest connected component? 3. Because 10-4-5 is the largest connected component. So we'll return 3 as the answer. Now with that being said, the only thing left to do is actually to go ahead and implement this. Let's get started with writing up the brute force solution. Again, it may seem useless, but it's going to form a huge part of our optimized solution. Let's get started with coding up the brute force solution. What did we notice before? Well, first of all, we want to iterate over all of the i's in range of n. We want to iterate over all the j's in range of n. And we want to do DSU.unite. We want to unite the indices I and j if and only if the nums of I and the nums of j have a GCD of greater than 1. And what do we want to do? At the end, we'll just return the maximum of DSU.sizes. It can seem a bit confusing, so I'm actually going to go ahead and show you how to actually code up the DSU part as well. Before that, a quick check is just to have n equals to the length of nums. And we'll also have DSU equals to DSU of n. Cool. Now we'll actually go ahead and write down the DSU function. I'm saying actually a lot, am I? Right. So what all do we need for the DSU function? Well, we'll need the size of the representatives and the sizes. So we'll call representatives equals to, initially in the DSU, we'll set all of the elements as their own representatives. So we'll just do this. Very simple. Also, I want to set the sizes equals to 1. So initially all of these connected components are just single element with themselves as their own representatives of the size 1. And this is the init part. Now, I also want to write down the find function, which given an index I want to find who the representative of that index is. So I'm going to say if self.representatives of I is not equals to I itself, well, that means that the current I is not its own king. It's not its own representative. So we'll have to go and find that. So let's go ahead and find the self.representative of I, and we'll store that in all right, then finally we'll go ahead and return the self.representative of I. I also want to write down the unite function or the merge function. I'm going to call it unite, and this is going to take in the input as I and j, which is going to be 2 indices. And we'll say, go ahead and find the representatives for I and j. So we'll say self.find I and self.find j. All right, what do we do once we have those representatives? Since we want to unite these 2 connected components, the first thing we'll do is check if I equals to j. Well, that means that both of them are already the same component. So we'll just return right away. If not, I'm going to go ahead and extract out the self.sizes of I. And I'm going to say, you know what, if the self.sizes of I is greater than self.sizes of j, I is greater than j, so I'm going to swap out I and j with j and I. Again, both of these tricks that I'm trying to do over here in unite and find functions are fairly common, and I'll link to resources down below. But this is a very, very standard implementation of disjoint set union. Nothing too special. All right, once we have both of these swapped, I can say that self.representatives of I. I've called it representatives. I'm gonna call it representatives. All right. Self.representatives of I becomes self.representatives of J, and self.sizes of J plus equals to self.sizes of I. All right, with this, we can go ahead and run this code. Right, find is not defined. Of course, it's not. Self.find. All right, good. It works with 49, 21, 10, 5, and 4. The case that we saw over here. Cool, yeah? So I'm fairly confident that this will work. I'm going to go run some sample test cases. And I'm going to go ahead and submit this and show you that it is going to give me a time limit error. I haven't tried it out yet though. And I highly doubt this is going to work. Cool. So we get time limit exceeded as we predicted. It's this order of n square loop is causing us a lot of issues. So in the next part, we're going to look at some observations and logic to actually how to start optimizing this order of n square into perhaps something better. Alright, let's talk about the observations and logic needed to optimize this solution. The first thing we note is, what are we doing up till now? What have we done? Let's try to write that down. We first took one number in order of n time. We first iterated over all the i's, then we iterated over all the j's, nested, and finally, once we had this nums of I and nums of j, we would compare both of them to give us the GCD. This is what we saw before, for I in range of n, for j in range of n, and then if the GCD is greater than 1, unite. Alright, it's fairly simple. How can we optimize this? What looks to me is the biggest time killer is for I in range of n and for j in range of n. Both of these nested for loops take the most amount of time. And so we want to focus our efforts on optimizing that part. Alright, so how do we think about that? Well, I want to think about now in terms of, can we change this order? We're taking one number first, then another number, and then finding the GCD. What if I instead want to swap the ordering of both of these? So I'm going to say, take one number, and instead of finding the second number and then taking the GCD, just find all of the factors for this number. And then we'll see what to do of the second number. But currently I want you to say, get me all of the factors for the current number. Right? Can you do that? It's very simple. So let's go ahead and take that example. We already saw this: 49, 21, 10, 5, and 4. This example as we saw before. If we write down all of these factors, if we write down all of their factorizations, we get something like this. So 49 gives 2 factors, 7 and 7, 21 gives 2, 3 and 7, and 10 gives 2 and 5, 5 gives 1, 4 gives 2 and 2. Right, nothing special. We've just written down all of the factors for each of these single numbers. So what I'm doing is I'm going over for num, go for I, num in enumerate nums, and I want to get the factors for the current num, and I'm going to write it as factors equals to this. All right, nothing too special, right? But if you notice, there's some repetition happening. There's some more compression we can do. There's things we can do to increase the efficiency. What can we do? If you notice, there are a lot of 7s that repeat, 2s that repeat, and 5s that repeat. So what if I write the entire thing in a more compressed manner? Something of this sort. The second row contains all of the same information as in this row, but it's just more dense representation. 4 is still linked to 2. 4 still gives 2 as the factor. Now since 2 was repeating twice, I just wrote it once because I want to more focus on the unique factors. Now 10 again gives 2 and 5 as we saw before, 5 gives 5. But now 4, 10 and 5 are able to get this compact representation of what was these 1, 2, 3, 4, 5 elements before. So we've converted these 5 intermediate yellow states to just 2 states. Similarly for the 21 and 49 case, right? Nothing too special. I wanted to pause and look at both of these for a minute. Do you recall something from before that had this sort of similar structure? If you realize, The brute force solution ended up giving this kind of answer, where we had a chain of 10, 4, and 5 on one side of one component, and a chain of 21 and 49 on the other side. What do you see over here? We see the exact same structure being repeated. 4 is connected to 10 via 2, 10 is connected to 5 via 5, 21 is connected to 49 via 7. Look at this again. Everything is exactly the same. It's just that we have written it in a different manner. The problem does not change. The intermediate state did change, and it's just a simple change in perspective. We haven't done anything special up till now, right? We've just, instead of finding two numbers GCD, we just wrote down all of their factors instead. That is all we've done. So now that we already know that these represent the connected components, how can we write that formally? Well, we know that for every single factor, there are going to be a bunch of numbers associated with that factor, right? 2 as the factor gives me 4 and 10 because 2 connects 4 and 10. Similarly, 5 as the factor gives me 10, 5 because it connects 10 and 5. Now there's one last thing that's happening. The most amazing thing of this question. If you realize, I can say for sure that 4 and 10 have a common factor. 4 and 10 will be two connected components, will be a part of the same connected component in the graph. I can say with 100% surety that 4 and 10 will be connected. Why? Because I'm looking at this list over here and it says that 4 and 10 are in the same list. Why are they in the same component? That's because both of them share the same factor 2, which is greater than 1, which means that all of the elements in this list of 2 will most definitely be connected to each other. And they'll be connected to each other. Why? Because all of them share a GCD that is greater than 1. All of them share a GCD which is greater than 1, which is the element 2. Right? Again, nothing too special. It's just writing down the problem in a different manner. And we've started to form something. Like, we can start to see our logic slowly being formalized. Now, if I ask the same question for factor 5, what can you say is the answer? For the factor 5, we know for a fact that 10 and 5 have to be connected. We know for a fact that 10 and 5 have to be connected. All right, so what's happening? The first thing we did was find out all of the factors, and then I'll also go ahead and form this data thing, which is going to be a default dict of list. And how is this going to work? Well, basically I want to iterate over a factor in factors. And for each of these factors, I'm going to say data of factor dot append the current I. Make sense? What I'm trying to do is I'm trying to get all of the factors for a given number num. I'm trying to find all of its factors as we did before. So 10 gives 2 and 5, 4 gives 2, 5 gives 5, 49 gives 7, 21 gives 3 and 7. I'm trying to first find all of the possible factors. For each of these factors, I'm going to add this same element inside of the data list. So now 3 as the factor will give me 21. 7 as the factor will give me what? 21 and 49. 2 as the factor will give me 4 and 10. 5 as the factor will give me 10 and 5. Right? I'm repeating things so that it's more and more clearer to you. We've not done anything special. We've just changed the way we looked at the problem. Nothing special. All right, let's finally come on to the last part of the solution. Now that we have these lists in hand, what can we do? Does the question, by the way, ask about these factors? It does not seem to care about the factors. Only the fact that, they have to be greater than 1 and that's it. So I don't care if it's 2 or 5 or 10 or 1000. I just care that these are factors greater than 1. All right, so I'm first going to extract these lists first. So I'm going to get data.values from this. I'm going to say for indices, in this, I'm going to do some computation. Indices is just going to give me this entire list of 4, 10 or 10, 5 and so on and so forth. Now I want to iterate over all the elements in the indices for I in range of length of indices. And I'm going to do this -1 over here because what I want to do is I want to do DSU.unite the indices of I with the indices of I plus 1. Right? I want alternate elements inside of this indices list to be paired up. I want 4 to be paired up with 10, and if there were another element, I want 10 to be paired up with that element, and so on and so forth. Right? Super simple. And this is exactly the part of the logic is exactly the same as DSU.unite I, j. But it's just that the I, j is in a different format now. All right, the only thing that's left to do is write down this get factors function. This is again going to be a very standard implementation. So yeah. We'll, by the way, start the factors from 2 because we don't really care about 1. So this if condition, by the way, then gets absorbed in this factor thing. And for I equals to 2, we'll also have answer as a set of elements. We really don't care about the repetition cases as we saw here. So 49 gives 7 and 7, but we don't really care about multiple 7s. I just care about 1 7, right? So I'm going to have an answer of which is a set, and we'll return the list of answer. All right, we're going to write down the while loop saying that I times I must be less than equals to num. Again, it's a mathematical proof that you can have this I basically iterating from 2 to the square root of num. So this is just a different way to write that. What to do now? I'm going to ask if num mod I is equals to 0, which means that I divides num. That's great. Answer dot add this current I, and num upon equals I. Else, if it does not divide it, increase it by 1. Right? So we started off with 2, and if 2 divides it, that's great. But if it does not, then increase the value by 1. Make it 3 and then try if num is divided by 3. So on and so forth, just keep on doing till I times I. All right, now I'm going to do a quick sanity check and we'll run the code. And I'm going to run some sample test cases. All right, it's fine. No need to get angry, man. All right, we'll go ahead and finally submit this. And hopefully this time it works. Cool. So we get a runtime of 5,000 milliseconds. By the way, I coded up the same thing, so it gives wildly different results, but the memory usage is always much better than everyone else. So yeah, anyways, this is it for the solution to the problem, largest component size by factor. This video took me quite a bit of time to write down, to create the visuals as well as to edit. So if you guys appreciate what I'm doing here, be sure to give it a thumbs up and subscribe if you haven't already. As always, thank you for watching, and I'll see you very, very soon.